Hello, this is Dr. Arterberg, and our presentation today is actuators in mechatronics. We will follow the textbook of mechatronics by Bolton, covering pneumatic and hydraulic actuators and mechanical systems. We'll talk about system, valves, cylinders. We'll talk about motion components and sizing of actuators. The main types of actuators that we work with in mechatronics include hydraulics. They are very high power. They require fluid control system, including pumps, valves, and filters. Also very common is the pneumatic actuator. It is considered as a lower cost, very fast, and also requires air supply and valves. Most commonly used in mechatronics, the actuators are electrical. They have a wide range of travel, force, precision, powered by rotary or linear motors. We'll see here an example of a fluid flow control. The signal comes in from the controller, and it controls the diaphragm set against a spring, which then would monitor the position of the stem to open and close the seat over here, which allows flow to go from inlet to the outlet. We see here an example of a hydraulic actuator controlled by a valve. We have a handle over here, and we have the pressure port, and we have the tank port. We have the possibility of having the system to be either in idle or in a position where we have the like we see over here on the right-hand side, the pressure connected to port A, and then the fluid goes into the top of the cylinder and pushes it down. While it pushes it down, then the hydraulic fluid is escaping through the bottom section into the tank. And as we move the lever to the right, this port is going to be connecting the pressure into port B, and then the fluid is going to go from the pump to the lower portion of the cylinder and go up, and the upper cylinder is going to evacuate the fluid into the tank. There are several types of valves. The reference, by the way, is listed on all the presentation pages at the bottom. And we see a large number of possible valves, gate, globe, check valves, ball plug, diaphragm, safety relief. Also, the application are stated over here by Wehrmacht. And notice that the pressure relief cannot be done by any one of the other valves. It has to be specifically designed for that. We also over here see some example of butterfly valves and also a ball valve. This shows us an example of an hydraulic system. We have in this example high pressure coming in here on the left. We have some relief valves. We have a monitoring gauge. We have a bypass over here that we can shut off these two valves and disconnect the flow in this section and have the bypass allow the flow to go to the right-hand side of the system. In the center, we have a control valve, which is controlled electronically by a controller that receives a signal from a pressure sensor at the point of interest and then it compares it within the controller to the desired set point, and then the difference is being acted by the filters. There could be proportional, integral, and derivative a combination, and then it makes a correction in the control valve setting such that the pressure will be as required by the set point. This shows us some examples of standard pneumatic actuators. These two are Parker and Festo, and quite similar. And what it looks inside, there is a piston. There is a piston rod that goes in and out. There is the housing, which is referred to as a barrel. There is one end port called the cup end port, and the rod end port where the air is coming in and out. To design a pneumatic system, typically the circuit diagram is being expressed by these symbols. We have here the pressure source, compressor, the cylinder with a spring return, a double acting with the two side. We have here double rods with a double acting. We have here a two position and a two-way port. We have over here a two position, 1 and 2, and we have three-way, 1, 2, and 3. Over here we have two position, and then we have four-way, 1, 2, 3, and 4. And this is a three position, 1, 2, 3, as we saw earlier, with four-way, 1, 2, 3, and 4. Here's some more examples of check valve. The fluid flow can go only in this direction. It's going to push the ball, which is set with the spring, but it cannot flow in the other direction. We have a flow control valve. We have a relief valve, which we talked earlier. These are main line and pilot line. A pilot line is a small flow controlling high flow of actuators. We see here a designation of a solenoid actuated cylinder. We have an internal pilot. This is the designation of a pilot, the small triangle, external pilot, and here we have a combination of a cylinder with a pilot and a manual actuation. And over here we see the solenoid as well. Here's an example of a design, conceptual design of pneumatic system. It has a compressor. It has over here a cooler to reduce the heat of the compressor. It has a filter. Then it has an air dryer, which goes over here to more pneumatic filters to make sure the air is clean. We have over here silencers. We have a solenoid valve, and then we have speed control valves, and then the two inlet to the cylinder are shown over here. Here's another example, air compressor in the circuit diagram, the air tank, the humidifier, and then over here the quality control device with the check valve. And then we have a filter and lubricator. And we need a lubricator to assure that the moving parts over here are going to be lubricated. So a mist of lubrication is embedded inside the flow and air. We have over here a spring, and we have a solenoid actuating valve, and we see over here three-way, and we have over here also the velocity control valves that control the air cylinder motion. This shows us a pressure regulating valve. Again, we have a adjusting screw over here against a spring that pushes on the valve stem over here, which opens and closes the inlet to regulate the pressure. The pneumatic solenoid valves are shown over here as standard components. We have the ports over here, and over here the electrical input to the solenoid. We see here an example how the pilot valve can control the directional valve. We see over here that flow comes in from this port into this port, and then the exhaust goes into this port. And then as the pilot valve would move either with a solenoid or with an external air source will move to the left, then the air is going to flow into the port and exhaust from the port 3. Here we see another example of controlling this is by Parker, controlling a cylinder in a vertical motion. So this here is a brake, and the brake is normally on when there's no system in a unit. And then you see over here that this valve is pretty much disconnecting it from any engagement to air. Now, as the air source applies a pressure, we see over here we have some check valve, we have relief valve, we have velocity control valves, and we have here solenoid actuated valves. And what we see here, that as the pressure builds here, then the pilot is going to push the brake valve to the right, and air pressure is going to be connected to the brake, and it's going to disengage the brake. Now, as long as there is a pressure, the brake is going to be disengaged. But as soon as the pressure comes down, then automatically the spring is going to overcome, and the brake is going to be engaged because the power is going to be disconnected. When we connect the actuators to a system, we have a PLC controller that commands through the Ethernet several actuators working together in some type of an automated process. And then for the actuator that the PLC is controlling specifically, each one of these valves is being actuated by a solenoid. Power is going to be supplied to each one of the valves. Air is going to be supplied, and each actuator is going to be commanded by the PLC through Ethernet. And then there will be cable management that will be providing also feedback of various sensors to the controller, including the emergency off. This is a button that has to be included in any automation system. We see over here an example of Festo XYZ pneumatics, which picking up with a gripper over here, picking up parts from a conveyor belt and putting them automatically inside a box. When we include the display into the system, we can receive data analysis again from Festo, moving into artificial intelligence and machine learning possibly. With this particular monitor is showing us the availability, performance statistics, and also the quality. The sizing of actuators is pretty much given by the vendors online. Festo, for example, is given online. You click on this button and you get to this page where you can a large number of electric and also pneumatic and servo-pneumatic positioning system can be automatically sized with the input by the user of the operating condition. Here's an example of such a result. The part number of a specific cylinder, which was calculated, is provided with an option also to click on a cart and purchase it online. Electric actuators are the most commonly used actuators in the automation mechatronic business. They come in various forms. We see over here a miniature stage by linear motor, driven by linear motor. There's only 2 parts to the linear motors versus 20 parts to a rotary motors, a very compact, very high performance made by Parker. We see another example over here of a ball screw stage. Sometimes it's called table, sometimes it's called an actuator. And we see the motor over here driving a ball screw. There's an encoder at the end, and there is a slide that can be used to mount other devices on it. We see combinations of electrical actuators in a gantry configuration. We see another gantry configuration. You see the cable management. And we see over here, for example, a DSP or dispensing device system that combines the gantry with a lot of peripheral equipment, and all connected to the controller and the amplifiers within an electronic box, which could be embedded within the system. Again, we see here the system that we saw earlier. We have here an XYZ dispensing system, which is controlled by a motion controller through a field bus. Each one of these actuators or axis is controlled by a servo amplifier, which driving with PWM, a motor. We have an encoder feedback, a limit switch, and there are also peripheral equipment such as a conveyor that may bring in parts to the dispensing system, and a robot that may take them from the box to the dispensing. And we may also have a camera, a human machine interface, and emergency machine off button again, and all commanded by the PLC to Industry 4 and possibly to the cloud. The application of electrical actuators are numerous. They include timing belts, indexing tables, the rack and pinion mechanisms, ball screw mechanism, various fitting mechanism, and they all may work as a mechatronic system with various sensors, which are part of the automation process. We see over here an example of several of these systems. We have here a ball or lead screw device, the indexing table, belt actuating device. Usually the specifications which are required in order to design a system like this. It's a more complex mechatronic system. Includes the motion profile which is required, the load, the transmission, the type of actuation, precision, and the environment. And when we do calculations as design engineers, we need to size the actuator, select its type, decide on the transmission, the motor type, the motor peak force, continuous force, power and voltage. And then in addition, we are often concerned about the stiffness, natural frequency, bandwidth, life, mean time between failure, mean time to repair, and cost, which we'll talk later when we discuss modeling and analysis. Here's an example of a small mechatronics device actuated by a motor, a DC motor driving a lead screw, which opens and closes a gripper for a robot. And then here we may do a model to simplify this kinematic and then use it for force and motion analysis. Some of the principles in analyzing a system like this include the sizing of a motor. And again, that will come in on a next lecture. But for now, we see that the motor is driving a mechanism, such as a ball screw and a load. And in order to size the motor, we have to find out what is the required velocity, as well as the required torque. Now, the torque is affected by the friction, as well as the inertia. And this here shows us the way we calculate the total inertia on the motor shaft in order to calculate the motor torque. The motor torque equals the total inertia times the acceleration. And the acceleration is determined by the various parameters of the ball screw or lead screw, and the inertia is determined by the various parameters of the load and the lead screw and the motor shaft. This shows us, for example, that to determine the reflected inertia of the mass on the motor shaft, which is one part, what we have to take is the kinetic energy of the moving mass, which is mass times velocity squared divided by 2. We see this over here. And we have to add to it the ball screw inertia times its velocity, which is the motor velocity squared, times divided by 2. And we also have to add to it the motor inertia multiplied times this angular velocity divided by 2. And then when we add all these terms together, we get the reflected inertia of the mass on the motor shaft, as well as the reflected inertia of the ball screw on the motor shaft. We add them together to get the total inertia. We see over here an example that when we go through the calculation, as shown over here, the details over here, the reflected inertia of the mass on the motor shaft is the mass times the pitch of this ball screw squared divided by 2 pi squared divided by the efficiency. Typically, a ball screw efficiency is 0.8, and a lead screw efficiency is 0.6 approximately. To find out the inertia of the ball screw or lead screw, for example, we have here the equation that the inertia equals to the mass times the radius squared divided by 2. And here we have another formulation which is helpful when we do calculation for boxes or plates. Similarly, we can see that in a mechanism of belts, which transmits from a motor to a lower speed belt with a pulley, we have going through this process calculating the kinetic energy of this pulley and reflect it over here to find the reflected inertia. Then we come up with a formulation that the reflected inertia of pulley B equals to the inertia of pulley B times the radius of the smaller pulley divided by the larger pulley squared. And similarly, when we have gear transmission, we have the same thing. We go through the formulation derivation, the reflected inertia of gear B on a shaft which drives gear A is given by the inertia of gear B about its own axis times the ratio of the radius of the driving gear divided by radius of the driven gear squared. The example over here shows us a more complicated situation where we have a load with a gear train. So the reflected inertia of this whole system, we take the load and we add to it the inertia of gear N. Then the equivalent inertia, reflected inertia on this shaft is this sum of them times the number of teeth of gear 3 divided by a number of teeth of gear 4 squared, and then we add to the inertia of gear 3 plus inertia of gear 2. We reflect it on the motor shaft by taking multiplied by the number of teeth or the radius divided by the number of teeth here or the radius of this gear, squaring it, and then we have this whole reflected on this shaft. And to find the total inertia, we add to it the inertia of gear N1 plus the inertia of the motor. And then we can continue calculating the motor torque by multiplying this total inertia times the angular acceleration of the motor. This shows us example of motor sizing of positioning system. This is done by Oriental Motor, but Parker, Festo also have online sizing tools. You see over here that we may come up with a configuration where we would like to size the motor for a certain process that requires a certain velocity with a certain load. We come in and we put in the total mass, the friction, whatever we have here as information for the bolt screw or lead screw diameter and the pulleys. And then when we click the button, we can come up with all the inertias as well as the bottom line required speed and required motor torque. This completes our presentation, and we'll talk more about it when we see next lecture how we size up motors. Thank you.